So part of the purpose in learning logarithms, as we saw earlier, it's frustrating when you get to a problem that you can't solve with your knowledge of exponents, and this helps give us something that can be an inverse operation of an exponent to help make some equations that seemed unsolvable or solvable only by guess and check to then actually be solvable. So these first two exponent equations here, you actually could have solved coming into this unit if you were good at manipulating numbers. And what I mean by that is these look a little crazy, but when you look closer, these are powers of the same number. So for example, in part A, I see a base of 1 over 125 and a base of 5. Okay? When I see these, I am thinking in my head, do these things have a commonality in the world of exponents? In other words, can they be written as a power of the same base? And they can. They can both be 5. This is 5 to the first power. This is 5 to the negative second power. I'm going to rewrite my problem using that idea. So instead of 1 over 25, I'm going to write it as 5 to the negative 2 power. I haven't really changed the problem. I've just written something in a different way but kept its value. The way that that helps me is now when I use my exponent power properties, and these can multiply, I have 5 to the negative 4n power equals 5 to the n minus 5. There's no way these powers that have the same exact base are equal unless their exponents are equal as well. So negative 4n must equal n minus 5. Okay? And if I go ahead and solve this, I would get that n is equal to 1. And I could plug that back in, and I could check to make sure that it works. So same idea here in part B. I'm looking at 16, and I'm looking at 1 over 32, and I'm asking, are those powers of the same number? And they are. 16 would be equal to 2 to the 4th power. And 1 over 32 would be equal to 2 to the negative 5th power. So then here, by my power property, I would have 2 to the 8n plus 4 equals 2 to the negative 5. And again, these powers with the same base are not going to be equal unless the exponents on those powers are equal, which means 8n plus 4 must equal negative 5. So I would get that this is equal to negative 9 over 8. So in these cases, we kind of use the strategy of rewriting the problem so that both sides were written with an exponential expression with the same base. Now, in these problems, it would be a problem. When I look at C, I see 5 and 823. I don't know a lot about the number 823, but I don't feel like it can be written as a power of 5. So I'm struggling there. And you can see in part D, we have bases of 3 and 5, and that's a struggle as well. So what I'm going to do here is I'm going to go ahead and take the logarithm of both sides of the equation. So I am going to take the log of 5 to the 3x. And I'm going to take the log of 823. Now, according to our power property of logs, having this power inside the log is same as having the exponent, multiplying the logarithm of that base, which means it can be rewritten like this. So that might not seem helpful, but it is because now you can isolate x. Now x is here. It's being multiplied by a 3 and a log of 5. And that's log base 10 of 5. That has value. You can type it into the calculator and see what it is. So I'm going to divide both sides by 3 times the log of 5. This factor will cancel out this one, and this factor will cancel out this one, just leaving x. And I will do that on the other side as well. And if I put that into my calculator correctly, I should get that x is equal to 1.39. And again, I can plug that in and check. A note here when you're putting this into your calculator, if you type log of 823 divided by 3 times log of 5, there should be parentheses around this so that the calculator knows that is all included in the denominator. All right, when I look at part D, the first thing that bothers me is that there is a square root on the outside. So I'm going to go ahead and square both sides of that problem. So here I'm going to get 3 to the power of 2x, and here the squaring of the radical would cancel their inverse operations. So I'd be left with this. Now, this is still bothersome because the bases don't match, so I'd go ahead and do what we did previously and take the log of both sides. And following suit in what we said and using that power property, this allows the exponents to then be written as products of the logarithm, so you kind of don't have exponents anymore, which is nice because we were having trouble getting x alone when it was in the exponent spot. Now here's a problem. There are x's on both sides, and I can't get them alone because this whole thing is multiplying this whole thing. So if I want to get the x alone, I'm going to have to kind of separate it from that minus 3. So I need to go ahead and distribute this number, this log of 5. Remember, that is just a decimal number here. So this is going to be x times log of 5 minus 3 times log of 5. And on this side, I have 2x log of 3. What I want to do is get all the terms with x on the same side so I can try and factor it out and get x alone. So I'm going to go ahead and subtract x times the log of 5 on the right side to cancel it. What we're looking to do here on the left side is combine like terms, but it's complicated because of the logarithms. So instead, I'll just write out what we have right now. We have 2x times log of 3 minus x times log of 5. And on this side, we have negative 3 times the log of 5. And so I can't really combine these together because of logarithms with, they have the same base, but I don't know what they're worth and what that would add up to. But I can factor out the x and see what would be left here to multiply that. And that is all numerical, meaning it's one big complicated number. But since this is all just one big complicated number and x is multiplying it, to get x alone, I can just divide by that large-looking complicated number. And if we were using no calculator, which our quizzes might be calculator okay, but our final exam in this unit will be no calculator, you would just leave your answer in this form. Here's what x equals, and you'd have this negative 3 log 5 over 2 log 3 minus log 5, and that would be okay. If you type that into the calculator correctly, you should get here that x is equal to negative 8.21. All right, so that's a summary of how we solve exponential problems when the bases are not the same. We use logarithms. But you can see it can be a little complicated. Try to keep track of your steps so that you don't lose anything along the way. All right, so here is a small application problem. Your MP3 player has about 126 million bytes of memory. Each month you plan to use 5% of the memory remaining. How many months will it take you to use a quarter of the memory? So notice that you are using up the memory, so the amount of memory is going to decrease by 5% each month. So using the formula that we had talked about before, given that it's decreasing at a constant rate, we would look at this, okay? And our starting or principal amount would be the 126 million, and the rate that it's depreciating would be 5% each month. Okay? And the question is, when would you reach a quarter of it? So you could figure out a quarter of 126 million. Oh, so see, our question is, how many months will it take us to use a quarter of the memory? Meaning the amount that we would want to have left is 3/4 of the memory. So you could do a side calculation to figure out what is 1/4 of the memory. And so you could do quarter of 126 million. And you get that that would be 31,500,000. And then if you then take that and subtract it from the 126 million, you get that there would be left 94,500,000. So the amount that would be left would be the 94,500,000. And for that to be the amount, the question is, how much time would had to have passed? And here we're using time in months. So then if I divide this, if I divide both sides by 126 million, you're going to see something happen that will be useful for future to save you some of the time that we just spent doing that calculation. And you'll see here that you get 0.75. Okay? We should have known this. Okay? We should have known that once we divided by the total, we would want this to come out to be 0.75, because we're basically saying we want 3/4 of the memory to be left. Okay? So that's what that should work out to be. So now we have 0.75 is equal to 1.05 to this power. So this is a lot like what we were working on with your contagion problem, and we were at a point where these are decimals. I'd have to do a lot of guess and check or something to solve. But now that we see the power of the logarithm in an exponential equation, we can take the logarithm of both sides of the equation All right, so we took the log of both sides. We have this, and to isolate t, we're going to divide by the log of 1.05. And so if you do this correctly in the calculator, except for I made an error. I'm sorry, you guys. Let me go back a couple of steps. Everything is fine except for that I should not have added together. See, it said subtraction up there, so this should not be 1.05t. That would be growth, and your memory is decaying on the device that you're using. So I just need to go back and change those to 0.95. Because 1 minus 0.05 would be 0.95. I'm really sorry. I'm sorry if you're erasing right now. And if you caught it, good for you. Okay, so we're going to go ahead and get 5.61. So that's how many months that it would take to get down to 3/4 of your memory. All right, now we're going to look at log equations. So some equations already come written like logarithms and how we would solve those. So if you look at these two here, it's very similar to the exponent problems where the bases are the same. You know, if we had 2 to the x power equals 2 to the 5th power, well, x has to be 5 in order for those to be equal. So the same idea here. If I have log base 2 of x equals log base 2 of 5, these are only going to be equal if x is equal to 5. So that's kind of the idea that we're using here. So in the first problem, part A, I set 2x plus 1 equal to 3x minus 5. And I go ahead and finish solving this, and I get x is 6. Now, in our log equations, it's super important to check because our logarithms had domain restrictions, meaning there were times that if we plugged something in, we literally could not calculate the answer. That's why the graph had a vertical instead of a horizontal asymptote. You couldn't plug in certain x values. So we need to double check that we can actually plug 6 back in to these equations. So when I do so, here is what I get. So I get log base 7 of 13 equals log base 7 of 13. Now, I don't know what log base 7 of 13 is, but that looks fine. So x is equal to 6. Now, when we look at this second problem, so same idea for part B, I'm going to set x squared minus 14 equal to 5x. This happens to be a quadratic. Please remember these skills. So we're going to move everything to one side of the equation, and we can factor or use the quadratic formula. This looks pretty factorable to me pretty quickly. So I'm going to go ahead and do that. I'm going to set each factor equal to 0 because of the zero product property. And I'm going to have two possible solutions, 7 and negative 2. Again, I want to check because logarithmic functions have domain restrictions. So when I plug in 7, let's see how this looks. I get log base 8, let's see, 49 minus 14 is 35. And on the other side, I have 35. And log base 8 at 35, I don't know it off the top of my head, but it's calculatable. So that's good. Now I'm going to check for negative 2. So when I plug that in, so negative 2 squared is 4. 4 minus 14 is negative 10. So log base 8 of negative 10, and on the other side, log base 8 of negative 10. This looks good because they look the same with our eyes. But what is log base 8 of negative 10? This is part of the stuff that's restricted from the domain. I can't calculate a logarithm of a negative number, which means this is undefined, and so this does not work, which means negative 2 needs to be eliminated from the solution set, and we only have 7 as a solution. Okay. So don't forget to check when you're solving these logarithmic equations. All right. Now, what if there's not logs on both sides? Well, when we were solving exponential equations, if we rewrote them with logarithms, all of a sudden, the variable was released from the exponent. Kind of the same idea applies here. Watch when we rewrite this as an exponential equation where the variable is. So if we rewrite this as an exponential equation, the base is 10, the power is 2, and that would equal 5x plus 2. Notice that x is no longer trapped inside of a logarithm when we did it this way. So this is going to work to solve this. Now I'm just going to solve it like it's a linear equation. So I get x equals 98 over 5. And I can check. So 98 over 5 times 5 would just be 98. So I'd have log of 100. And that is true. Okay. All right. So in part D, I have log base 10 of z plus log base 10 of z plus 3 equals 1. So first problem here is I do have two logarithms, but I also have a constant on the other side that's not part of a logarithm. So I'm going to go ahead and combine together the two log base 10s. I can do that using the product property. The z will be multiplying the z plus 3 inside of this one logarithm. So I have log base 10 of z squared plus 3z equals 1. And now I'll rewrite this in exponential form. Again, this is a quadratic, so I'm going to go ahead and get all the terms on the same side of the equation. And factor if possible. Here it is. And then I'm going to set each of those equal to 0 to find the possibilities for z. So z can equal negative 5 or 2. So I'm going to go ahead and check. So I'm going to check negative 5 As I'm checking, I'm kind of noticing a problem right away. Right here, log base 10 of negative 5, the way that's entered in, that's undefined. So negative 5 is not going to work. Now, it's not that always the negative solutions don't work. It's if you plug them back in and you're trying to take the log of a negative that they don't work. Okay? So that one doesn't work. And now I'm going to check when z is equal to 2. So that looks like log base 10 of 2 plus log base 10 of 5 equals 1. If we did combine these together, we'd get log base 10 of 10. And that seems fine. And there was no place along the way it was undefined. So I'm going to eliminate negative 5 and just keep that z should be equal to 2. So remember that since logs and exponents are inverses of each other, they're useful tools. And when you're trying to get a variable out of an exponent, use a log. If you're trying to get a variable out of a log, use an exponent because they undo each other, just like multiplication and division or addition and subtraction.